Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems from the question paper CSIR National Eligibility Test held in the month of March 2025. It is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Algebra, and the question is from group theory, and it is related to the conjugates of the elements of a subgroup H. And this question is placed in part B, which is a multiple choice question. It carries 3 marks. The question ID is 706518. Further, this question is suitable for all these examinations. Right. The given question is, let G be a group of order n greater than 3 and H be a subgroup with 1 less than the order of H less than n. That means H is not the identity and H is not the whole of the group G. Consider the set capital X is equal to the union G H G inverse where G belongs to capital G. That means the union of all conjugates where small g belongs to G. The union is taken over all the elements of capital G. Which of the following statements is true? Option 1. If G is abelian, then order of X is n. Right. Option 2. If order of X divides n, then G is abelian. Option 3. Order of X less than n. Order of 4. Order of X divides n. Let's now discuss the solution of the problem in detail. We have a group G and its order is n and n is greater than 3. Let H be a subgroup of G and 1 less than mod H less than n. That means H is not the identity element alone and H is not the whole of the group G. Right. Given X is the union of small g H capital H G inverse where the union is taken over all elements small g belongs to capital G. And it is the union of all the elements G H G inverse where small h belongs to capital H, where the union is taken over all the elements of capital G. It is the union of all the conjugates of the elements of the subgroup H. Each conjugate G capital H G inverse, it is known, it is a subgroup of G and its order of G capital H G inverse is same as order of H. These results are very well known. Let us now talk about option 1. If G is abelian, then order of X is equal to n. Is it so? Now, G is abelian This implies for any G belongs to G, we have G capital H G inverse is equal to G set of all G small h G inverse, small h belongs to capital H. And because G is abelian, the elements can be commuted. This is equal to the set of all G for GH, we have written G inverse, where small h belongs to capital H, and G inverse is identity, H into identity is H. So it is the set of all H belongs to H, that is H. That means the order of X is equal to the union of G belongs to G, G inverse. For each G belongs to capital G, G inverse, G capital H G inverse is H only. The union of all these H is H only. Therefore, X is H. The order of X is order of H, but the order of H is less than n. Therefore, the option 1 is not true. In option 1, it is given order of X is equal to n, but we got order of X less than n. Therefore, option 1 is not true. We move to the next slide. Option 2. If mod X divides n, then mod means norm the order of X divides n, then G is abelian. Let we give a counter example. Let G be the dihedral group D4. The order of D4 will be 2 into 4, 8. So let G is equal to D4, the dihedral group, and its order n is equal to 8. It is well known. It is non-abelian. Let us take capital H with a subgroup generated by rho square, where rho is a rotation of D4. So, and the rotation, what are the properties of rotation? Rho power 4 is identity. So, it is the subgroup generated by rho square consists of elements E comma rho square, because rho power 4 is identity. So it is a subgroup of G. It is a subgroup of D4 of order 2. For any G belongs to D4, we have G rho square G inverse is also rho square. Why? Because rho square belongs to the center of D4. Right. So thus, for all G belongs to D4, G capital H G inverse is the set of all G E G inverse, comma, G rho square G inverse. And that will be G E G inverse is E, G rho square G inverse is also rho square, so it is H only. Right. X will be the union of G capital H G inverse, where G belongs to G, the union is taken over all G belongs to G, it will be H only. The order of X will be order of H. Order of H is 2. Order of H is 2. So now order of X is equal to 2. It divides n is equal to 8. Order of X divides n. But G is equal to D4 is not abelian. So if order of X divides n, then G is abelian is not necessarily true. Here is a counter example. Therefore, option 2 is not true. Right. We move to the next slide. Option 4. Order of X divides n. Yeah, we feel this is not true. Go for a counter example. Let G be S3, the symmetric group on 3 letters. Its order n is 6, 3 factorial, that is 6. Let H be the group generated by the transposition 1, 2. So this is, who are the elements? 1, 2. 1, 2 square is identity. So H is the subgroup generated by the transposition 1, 2 consists of elements E and comma the transposition 1, 2. H is a subgroup of order 2 of the group S3. A conjugate of H is a subgroup of S3 of order 2. Right. How many subgroups of order 2 are there? If you look into S3, there are precisely 3 subgroups of order 2. What are they? E, comma 1, 1, 2, set consisting of. Other one is set consisting of E, comma 1, 3, that is transposition 1, 3. The third one is the set consisting of E, comma the transposition 2, 3. These are the only 3. And any conjugate of H is a subgroup of S3 of order 2. And there are precisely only these 3. Therefore, the conjugates of H, so therefore the conjugates of H are these only. The conjugates of H. So therefore, X is equal to the union of G, capital H, G inverse, where the union is taken or all G belongs to G, will be the first subgroup, union, the second subgroup, union, the third subgroup. That will be the set consisting of E, comma, transpositions 1, 2, 1, 3, 2, 3. What is the order of X? It is 4. But the 4 does not divide n, that is 6. So the order of X does not divide n here. But what is given? Order of X divides n. This is not necessarily true. In this case, this fails. Therefore, option 4 is not true. So far, we have shown options 1, 2 and 4, and we have seen they are all not true. By elimination, option 3 must be true if the given example is true. So not only that, from this option 4, what are you seeing? Mod X, the order of X is for less than n. That is precisely our conclusion of option 3. Therefore, through this above example, we get a feel. The order of X is less than n. That's how we guess option 3 is true. Right. So the question is over, but we'll prove option 3 is true in the next slide. Option 3. Order of X is less than n. Note that E belongs to GH inverse for all G belongs to G. The total number of distinct conjugates of H is equal to the index of the normalizer of H in G in G. G is to the normalizer of H in G. That is the index. Where the normalizer of H in G is a set of all G belongs to G such that GH inverse is equal to H. This is the normalizer of H in G, what we have studied. And with this definition, if you take any element from capital H, small h, capital H inverse will be H. For all small h belongs to H. That means every element of capital H will be there in the normalizer of H in G. Therefore, the order of the normalizer of H in G is greater than or equal to order of H. Right. This is very crucial. This is what we require. Let the distinct conjugates of H be H1 is equal to H, H2, etc., HR. Where R is the index of the normalizer of H in G. The G is to N or N of H in G. They are the distinct conjugates of H. Then X will be the union G capital H G inverse, where the union is taken over all small g belongs to capital G, will be all conjugates. Who are they? H1. H1 is equal to H union H2 union HR. Right. H1 is equal to H, not union. This is H. H1 is equal to H union H2 union HR. So that means they are precisely H1 union H2 union HR. So therefore, what will be the order of X? The order of X will be number of conjugates, that is R, into the number of elements in each conjugate. In each conjugate will have order of H elements. Why less than? Why less than? Because they overlap at least at identity. That means each element, each conjugate, that is H1, H2, HR, they have a common element, that is the identity element. Therefore, the union of all these things will fall down, and that is how the order of X is less than R times order of H, because they overlap at least at identity. Not even less than or equal to, it is strictly less than. Right. Now calculate order of X is less than R times order of H, that is equal to R. R is the index. The index of the normalizer of H in G. G is to NHG multiplied by order of H. And since order of G is finite, this index is order of G by the order of the normalizer of H in G multiplied by order of H. Order of H. But you know, the order of normalizer of H in G is greater than or equal to H. Here it is. It is greater than or equal. Therefore, order of G by the order of the normalizer of H in G will be less than or equal to 1 multiplied by H, mod H, the order of H, order of H. No. Order of G is N, and order of the normalizer of H in G is greater than or equal to order of H. Therefore, order of H by the order of the normalizer of H in G is less than or equal to 1. Therefore, order of G is 1. So, is less than or equal, order of G is N, is less than or equal to N. But it is less than followed by less than or equal to N. Therefore, order of X is less than N, strictly. Now you see, this is less than 1. Order of H by order of the normalizer of H in G is less than 1, less than or equal to 1, because the normalizer of H in G, the order is greater than or equal to an order of H. Therefore, it is less than or equal to order of G. Order of G is N, is less than or equal to N. Less than followed by less than or equal to, therefore order of X is less than N. Thus, option 3 is true. Summarizing all the options, the answer to this question is option 3. That is the detailed discussion of the solution of this problem from the section algebra, from group theory, and it is related to the conjugates of the elements of a subgroup H of G, where G is a finite group. In my opinion, answering this question in the examination will be a difficult task, for me at least. Getting those counter examples in the examination hall will be very difficult. But anyway, such questions do occur once in a while. If it is possible, we do it in the exam. Otherwise, we leave it. That's the best strategy. Right. I'm sure that you understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, we will meet once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.